Hi, my name is Christopher Chubb, and welcome to my talk today on general tensor network decoding for 2D Pauli codes. I am currently a postdoc at ETH Zurich, and today's talk is about work I mostly did at the University of Sherbrooke. Before we begin, a brief overview of the structure of my talk today. I'll start by talking about the problem of decoding quantum codes in the presence of Pauli noise, and then move on to showing how this can be reduced to a tensor network problem. I'll then talk a little bit about existing tensor network contraction schemes. I'll highlight some of their limitations and how my new Sweepline Contraction algorithm circumvents many of them. I'll then introduce the numerics performed to test the practical usefulness of this approach, as well as the results. And then I'll conclude by recapping and mentioning some possible future work in this direction. I'm going to start by looking at the problem of decoding Pauli noise. A naive starting point when it comes to decoding an error is to ask, given whatever syndrome data we have, which is the most likely error to have occurred. To answer this, we first need a noise model. For stochastic noise, this takes the form of a map from possible errors to their associated probabilities. This might take the form of an IID error model, where qubits are independently afflicted by noise, or a more complicated model capable of accommodating correlations between errors at different points in space or time, but for the moment we'll just consider some general Pauli noise model. If we consider the distribution that this model describes, then the solution to the question of the most likely error is simply answered by taking the maximum over this distribution. For classical codes, this would be the end of the story. Quantum codes, however, exhibit degeneracy, wherein multiple errors can be indistinguishable and yet have the same logical effect. To account for this, we need to group degenerate errors into so-called error classes. We can now see that we should refine our question into not what is the most likely single error, but what is the most likely error class. To do this, we need to find the induced distribution over these error classes, and once again, take the maximum. For Pauli errors, this approach is in fact optimal, and it is known as maximum likelihood decoding. From a practical perspective, the most difficult part of maximum likelihood decoding is evaluating these error class probabilities. We can see this by expanding their definition, which involves a sum of all degenerate errors within each class. For a stabilizer code, this can be rephrased as a summation over the entire stabilizer group, with analogous expressions for other code families such as subsystem codes. Even if the probability of an individual error has a simple closed form, such as for IID error models, the exponential size of this sum makes evaluating their class probabilities typically impractical. So far, we've looked at decoding in the abstract. Now we're going to turn our attention to how one might go about actually implementing it. The approach we're going to look at relates the error class probabilities of our code to values of a tensor network. The idea of a connection between quantum codes and tensor networks can be traced back as far as this 2013 paper by Ferris and Poulan. In 2014, Bravi, Suchar, and Vargo showed how such a connection could be leveraged for the purposes of maximum likelihood decoding. Their paper specifically focused on the surface code and only considered IID noise. More recently, in a 2018 paper with my PhD supervisor Steve Flamia, we were able to extend this connection. This was done by first mapping the codes to classical statistical mechanical models, and then in turn to tensor networks. This approach had the key advantage that it worked generally for any Pauli code, and even allowed us to incorporate more complicated noise models such as those involving correlations. So, let's be concrete about how this mapping works. This mapping relates three different quantities. The first are the error class probabilities of a local code. As we've seen, calculating these is key to optimal decoding. The Second are the partition functions of a local StatMech model. And then finally, we have the contraction of local tensor networks. Importantly, the locality of the underlying code is carried through this procedure. By this I mean, if we were to start with a 2D code, then the StatMech model and the associated tensor network which result are both also two-dimensional. For the sake of brevity, I'm not going to cover the full construction of this tensor network in this talk, and I would redirect you to my earlier paper on the StatMech mapping for a discussion of this. But, for illustrative purposes, I'll try to give you a sense of what this mapping does by looking at the example of the Steen code. The Steen code consists of 7 qubits arranged into 3 faces. For this code, we have a tensor for each qubit, as well as a tensor for each of the stabilizer generators, which live on a face. As you can see, the tensor network is naturally imbued with a connectivity structure very strongly related to that of the original code. So far, I've shown how the problem of 2D decoding can be reduced to that of contracting a 2D tensor network. So, is this an easy problem? Well, no such luck. In 1D, contraction is easy, as it's essentially the problem of matrix multiplication. In 2D and beyond, however, the problem of exact contraction is sharp P complete. But whoever let complexity theory get in the way of a good time? Instead of hoping for an exact contraction scheme, what about heuristics that will allow us to approximate contraction? The trick here is going to be to utilize techniques from 1D tensor networks to attack the 2D problem. The key to the algorithms we're going to consider are an important class of 1D tensor network states known as matrix product states, which consist of a daisy chain of tensors arranged in a linear fashion such as this. These internal connections within the MPS are referred to as their bonds, and their dimension as the bond dimension. As long as the bond dimension remains bounded, storage and manipulation of MPS remains efficient. This bond dimension is going to control the quality of the approximate contraction algorithm. An important property of MPS is that they omit a procedure known as bond truncation. Bond truncation allows us to find low bond dimension approximations to MPS states, essentially acting as a lossy compression procedure. So, as I've alluded to, the idea is going to be to reduce the 2D problem down to a 1D problem. The approach we're going to consider originally arose in the context of the condensed matter literature in this paper by Verstraete and Serac. In the context of decoding, this algorithm also formed the core of the aforementioned paper by Bravi, Suchar and Vargo, as well as 2 follow-up papers from the Sydney group. So, let's see how this algorithm works. Suppose we have a square lattice tensor network. We start by interpreting the leftmost column of this network as an MPS. Next, we can consider pairing up the tensors in the MPS with those in the next column and contracting them together. In doing so, we can see that the dimension of these bonds has grown. Specifically, the dimension is squared. Left unabated, this growth is going to lead us to an exponential time algorithm. But this is where we can speed things up by relaxing from an exact algorithm to approximate. As you may have guessed, we do this by applying the bond truncation procedure, bringing the dimension down to a manageable level. We can now simply repeat this procedure for each column until we're left with a 1D network. This, in turn, can simply be evaluated by performing matrix multiplication, leaving us with our answer. Now I'm going to turn my attention to the main new technical tool of this work, a Sweepline Contraction algorithm. Before describing the algorithm, let's first go over some of the limitations of the Verstraete-Serac algorithm that it alleviates. Both of these limitations come from the column-by-column nature of that contraction algorithm. Firstly, while one can imagine generalizing the notion of columns to other regular lattices, what about irregular networks, such as random triangulations. A second and more subtle question is that even if these columns are well defined, how do we find them algorithmically? One approach is to simply coarse-grain our lattice into the square lattice. Here's an example of this from a figure in Tuckett et al. For the case of the rhombile lattice. This approach, however, is rather clunky, and it's far from obvious how one could automate this. To circumvent both of these limitations, the Sweepline Contraction algorithm eschews columns altogether. The result is a contraction algorithm which will function on any 2D graph, not requiring any manual preprocessing of the graph at all, allowing it to be easily applied to complex lattices or even randomly generated networks. Before we go to the contraction procedure, let me briefly review what is meant by a Sweepline algorithm. Sweepline algorithms are an algorithmic paradigm largely used in computational geometry. These algorithms process data which has some geometric nature, which allows it to be laid out in the plane. The idea then is to consider an imaginary line passing across the data. This approach is most useful when a partial solution to the problem can be maintained, only requiring access to objects in the vicinity of the sweep line to update this. This has the effect of reducing an essentially 2D problem down to 1D, which was exactly our goal. So, what does a sweepline-based contraction algorithm look like? We start by laying out the 2D tensor network in the plane, and we're going to sweep across this network, updating whenever we hit a tensor. When we hit the first tensor, we split this into an MPS. We then consider sweeping along to each tensor, contracting that tensor into the MPS, and then reforming the MPS structure, performing bond truncation where necessary. This procedure is repeated, maintaining an MPS approximation of the left half of the network. Once the entire network has been passed over, we're once again left with a single number, which is our output. So, now that I've introduced the sweepline contraction algorithm, how well does it work? To demonstrate the flexibility and efficacy of this tensor network approach, I tested it against 13 exemplary 2D quantum codes, each subject to 3 different noise models, giving a total of 21 independent thresholds. Before we come to the codes, let's consider the 3 error models we're going to test them against. Firstly, the bit flip channel, which randomly applies a Pauli x with probability p. The phase flip channel, which randomly applies a Pauli z. And finally, the depolarizing channel, which randomly applies a non-trivial Pauli. We note that all of the codes we're going to consider are CSS, allowing them to simultaneously correct X and Z noise, meaning that the bit flip and phase flip data we get also tells us about BB84 type channels that consist of both bit and phase flip simultaneously. Okay, so now onto the codes. The main class of codes we're going to consider are surface codes. These are generalizations of the toric code defined on any planar graph. Specifically, these are codes with qubits on the edges of such a graph, with Z-type stabilizers residing on the faces, and X-type on the vertices. As a test, we start with the surface code defined on the square lattice. We then consider 3 dual pairs of lattices, the first being the triangular and hexagonal lattices, the second being the Kagome and rhombile lattices, and then finally the truncated hexagonal and Asanoa lattices. As well as these 3 regular lattices, we also consider 2 dual pairs of random graph families, namely random triangulations and random trivalent graphs, and random quadrangulations and random tetravalent graphs. Lastly, to demonstrate our technique can work for codes outside the surface code family, we also consider two other codes, namely the color code and the subsystem surface code, a non-commutative variant of the surface code. And now we turn to the numerical results. Here is a table of all the threshold estimates. The rows correspond to the different codes arranged into regular surface codes, irregular surface codes, the subsystem surface code, and finally the color code. The columns correspond to the three noise models, namely bit flip noise, phase flip noise, and depolarizing noise. For each of these, we have the numerically observed thresholds alongside theoretical upper bounds where known. In each of the cases where such upper bounds are known, the observed thresholds are within several error bars, suggesting we are well approximating optimal decoding. And what about the gaps where the upper bounds are not known? Is there some indication we can use to compare our thresholds to their optimal values? Well, for the bit flip and phase flip thresholds of the surface code, it just so happens that there is. It's conjectured that the surface code under bit and phase flip noise will saturate something known as the zero rate hashing bound, giving a trade-off between the X and Z thresholds. Here, tau represents these two thresholds, and H the binary entropy. We can now test our data against this conjecture, comparing with earlier data from Fuji et al. Using a suboptimal decoder known as minimum weight pair matching. We now include our data for the regular surface codes and irregular surface codes. In all of these cases, we can see that our data lie very close to the hashing bound, suggesting all of these thresholds are in fact very close to optimal. To quantify this, we can look at the entropies associated with these points, finding our data to be in very strong agreement with the conjectured bound of 1. And now we've come to the conclusion. In this talk, I've introduced a scheme for tensor network decoding of any 2D Pauli code, and numerically demonstrated this scheme to be both highly flexible and highly effective. Several extensions of this work suggest themselves in making this decoder more widely applicable. The two most obvious are including noisy measurements or going to codes beyond 2D, both of which I'm currently working on. There are also several other potential directions, such as more general noise models or optimizing the runtimes. The paper is available in the archive. Here are my relevant links if you want to get in contact with me. Thanks for listening.